Good afternoon, everybody. So we are starting our session. In this session, we are learning blockchain platforms, multi-chain blockchain, Corda, OpenChain, and Solidity. Over to you, sir.
Thank you. You'll have to give me
Yes, sir.
screen.
I'm doing the same. Just a second.
Sure.
So now you can do it.
Thank you. So coming back to our high-level discussion on Hyperledger. So we talked about how Hyperledger is geared towards a business scenario where we create a business network that is focused usually towards a specific domain. And the typical scenario in which such a business network operates is that there will be a group of companies that are going to get together, all of them um, in business in a specific domain like supply chain companies or healthcare companies or banks. And what they will do is they will set up a business network of which they will be a part of. More specifically, they will have at least one node that will run that business network as a Hyperledger instance. And the core logic. So if we think about um, any business process, there are two parts to that process. One is the core asset on which the process works. I mean, you can think of it as anything that uh, that business is supposed to process. It might be a service, it might be a real tangible asset, it might even be something intangible as securities or stocks or uh, bonds. So all of these, they constitute the asset. And then the actual processing that happens on the asset could be the functions or interactions or transactions that um, this process is going to implement on top of this asset. So if we talk about stocks, then some of the processes would be issue a stock, sell a stock, um, retrieve stock balance, or delete a stock or dissolve a stock. So almost all business processes can be represented in this way, where there is an asset and there are some processes. Um, Once you've identified these, then Hyperledger recommends that you create a set of contracts, which are basically um, programming business logic uh, components that represents these assets defined as field level variables, and then operations or transactions defined as methods. So if we talk about a business network for, let's say, car manufacturing, then the asset would be the car. And then, I mean, so there'll be a lot of other assets, but in a very simple, easy to understand scenario, the asset would be the car. And you you would implement a smart contract that will define a car, maybe with 4 or 5 parameters. And then the processes that can be done on a car, maybe apply, um, maybe manufacture or assemble, and then ship and store. I mean, whatever happens in a typical automobile manufacturing life cycle, all of those would be the processes or functions that you implement. Now, Hyperledger allows you to build these smart contracts or chain code in multiple languages, multiple programming languages. So you could be using JavaScript if you're familiar with JavaScript. You could be using Golang, which is a language open source by Google. Or if you're familiar with Java, then you could choose Java. What Hyperledger does is it creates an environment for your smart contract or chain code to execute that is specific to the type of uh, technology stack you have. Having said that, this is where Ethereum and Hyperledger are again different. So the first thing that we talked about was the modularity. Hyperledger supposes that um, your entire blockchain uh, software stack, it should be modular. Different parts of the blockchain um, execution process should be taken care of by different modules. Ethereum doesn't propose that. The other difference is Hyperledger allows for different types of programming languages for building chain code. Ethereum just has one programming language, not really one programming language, but one instruction set. There are more than one programming languages that are compatible with Ethereum, but all of them compile to the same instruction set that Ethereum environment understands. Ethereum environment is also called Ethereum virtual machine, in which the smart contracts execute. So although Ethereum supports multiple languages, but the environment is the same. On the other hand, Hyperledger gives you environment for JavaScript, which is completely different than the execution environment for Golang. And then Java is obviously, again, very different. So one of the most important components in Hyperledger Fabric is the orderer. Talked about what are the modules, orderer, membership services. These are some of the modules. But the most important one is orderer. So orderer maintains a list of organizations or list of entities that are a part of the network. And then it enforces some basic access controls when you are accessing the network. So accessing the network, what that means is you're basically trying to call the chain code or smart contract that you've deployed in Hyperledger. And all of the access control that has to be applied to your call. That is, if you are allowed to call that smart contract or not, if you are allowed to read the transactions that you're trying to read or not. All of that enforcement is done by orderer. And orderer basically in its role of sequencing and controlling transaction access provides three pluggable consensus mechanisms. So as we have been maintaining, Hyperledger is about modularity and plug and play. So you can plug these different kinds of consensus mechanisms within a Hyperledger instance uh, using the same principle of plug and play. So Solo is a type of consensus that assumes that it will be a single organization business network. What that is typically used for in testing. You would obviously, if you want to build a blockchain, you will have multiple organizations. And then there are two production grade consensus mechanisms. First is called Raft. So Raft is, and those of us who are into distributed computing will understand what Raft means. It is an election based logic which um, allows for random selection of leaders in a distributed computing environment to accept um, transactions and blocks. And then Kafka, which is also a leader and follower um, based mechanism, is again a crash fault tolerant system that allows for uh, accepting transactions and sequencing them correctly. So with that input, we can take a look at how, and this is something that we want to do for Ethereum as well. We can take a look at how a typical Hyperledger instance looks like. So at a very high level, there are two parts to this. One is the client or the transaction initiator, and the other part is the Hyperledger blockchain. On the client side, what you will have is an application that is user facing. And that application will be built as an implementation of what is called the Fabric SDK or software development kit. So there will be a language specific software development kit that will allow you to implement a user interface and middleware logic that initiates transactions. On the ledger side or on the blockchain side, the first thing that that transaction is going to reach is a specific kind of node or peer. It's called the endorser peer. And what that endorser does is it checks for the authenticity that you have in the transaction, the right transport layer security, you have the right digital signatures. Once all of that check is done, the transaction goes back to the client with an endorsement. Endorsement is like an approval. And then that approved transaction goes to the node, uh, which represents the ordering service. That's that green node. And from here, it gets sequenced based on the consensus we selected. And then it goes to a committer node instance, which is like a regular peer that executes the smart contract and updates the blockchain. So this is the high level transaction flow for Hyperledger Fabric involving the client and what happens on the ledger or the blockchain side. Now, if you want to understand this in a different way, there are, so if you want to kind of decouple the components of the transactions a little further. The application is the one where the transaction comes from. The application can directly go to the peer also if they want to read something about the blockchain, where all they have to do is just authenticate themselves, and they are not looking to execute any contract. They just want to read the blockchain state, the data on the blockchain. Then they can go to the peer directly. If they want to execute a smart contract and they want to send that as a transaction that basically updates the blockchain, that's when they have to get it endorsed and sequenced in the right way. So they have to go through the orderer route. Now, once, and we will do this in the coming sessions, once we deploy a test blockchain, a test Hyperledger instance, we will actually see this happening where we'll call a contract and then execute um, different functions in the contract directly from our client. So the other important parts of Hyperledger are the membership provider, which is basically that endorser node that stores the cryptographic material that represents different entities on the Hyperledger fabric. And the other part is the channels. So channels are like an abstraction of a communication route. When a Hyperledger instance is set up, the only way to communicate with that instance is by creating a channel. And a channel is a group of entities that are part of the Hyperledger business network, but who just want to talk amongst themselves. So a Hyperledger instance can have more than one channels. And to equate this with a real world example, if we're talking about, let's say, a supply chain network, then a channel in that network might be distributors channel, where all the distributors communicate with each other. The transactions in that channel are not visible to other parts or other entities on the network. Similarly, there could be a shipping company's channel where all shipping companies interact with each other. So all the transactions that are specific to a channel are only visible to the channel that they belong to. And then finally, the smart contract piece. So as stated, we could Hyperledger basically supports 3 different environments in which smart contracts can run. And one thing that needs to be understood about Hyperledger is that it runs in container environments. More specifically, the Docker container. What that means is that the Hyperledger compiled code, as in all of the different components like peer software and the orderer software and the MSP and channels and everything, they are run as container images. For those of us who are familiar with containers, they will know what I'm talking about. Containers are virtual machines or very similar to virtual machines where they offer a universal environment for a software component to run on any platform. So for example, if I want to build software for Windows, and if my software is container compatible, then the same compiled code can run on Linux as well, or it can run on Mac OS X as well. So Hyperledger is compiled as container images. And when we'll run Hyperledger sample code, we'll take a look at how Docker is utilized in that. Now, the very fact that we are using Docker allows us to support different kind of language environment, not us, Hyperledger. So Hyperledger can basically pull the environment for running JavaScript code or Java code as an image in the Docker container, and then that image can help support running that smart contract. Ethereum, with its native software, that is software that's not directly Docker compatible, although they have Docker software. But Ethereum has to build a virtual machine itself, the Ethereum virtual machine, so that smart contracts can execute inside it. So this is one sort of point of comparison between Hyperledger and Ethereum. So having said that, all that we talked about today, we will also see running both on the Ethereum front and on the Hyperledger front. The only additional thing that I want to show you about these two is the ability, or really the way in which the Ethereum applications look like. And let me see if I can pull up a deck to show that. Give me one moment. Right. So I wanted to bring this up for like the general blockchain discussion as well. All the applications that we build on blockchains, they're called decentralized apps or DApps. And these applications are they're basically more decentralized when they're built on public blockchains, which is why the term DApps is more frequently heard when we're talking about Ethereum or some of the other smart contract blockchains like Solana or EOS, because these applications are decentralized in their true nature. They are deployed on all the network nodes. So what is a decentralized application is a combination of two things. One is the smart contract, and the other is the client that is calling the smart contract. When it comes to Ethereum, the technology stack or the flow, it looks something like this. So you've got the blockchain on which your smart contract is deployed. And then you've got the node software that basically interacts with the blockchain. Usually we use the Golang node software called Geth. And although we are fully capable of installing Geth on our systems, but because of the bulky nature of blockchains and the memory and software requirements, we usually use um, public nodes. These are nodes that basically are available for developers to use, on which the blockchain node is pre-installed. You just have to call them through their APIs. So this is this whole box. This is the blockchain part of it. And what we've got here, which could be a web app or mobile app or iPhone app integrated with a wallet software, usually MetaMask, is the client. So you've got this one line in between. On the right side, you've got the blockchain infrastructure, which will be most of the times remote. And on the left side, you've got the client software and the client experience. From a technology standpoint, and we'll take a look at this again because we've not really got to the technology part of it. But on the client side, we usually use J or JS, which is Java or JavaScript libraries. Ethers.js is the most popular one. Then a wallet software, which could be like a browser extension or a mobile app. And then on the public node side, we use Infura or Matic nodes. Matic is a layer 2 solution called Polygon. And then the languages that we use for building smart contracts usually are Solidity and Viper. Now, having said that, this is the scenario very, very specific to Ethereum. Although it looks similar to what we saw when we were talking about Hyperledger, there is the client and the blockchain side. The technology set is very, very different. The only common thing you'll find is JS. So, which is why we are going to be sticking to JS when we'll do our demonstrations, because that way, with one technology understanding or one programming language understanding, we'll be able to manage, uh, we'll be able to see both Hyperledger and Ethereum operate. So having said that, what I will now jump to is a high level um, description of some of the other frameworks. The most interesting one is IOTA. And then um, there are some other frameworks we'll talk about. But I'll take a quick pause for any questions that you might have. Feel free to type them or speak out, whatever you're comfortable with. All right. In that case, let's talk about some of the other blockchain frameworks that that are kind of similar to the frameworks that we've already discussed, Ethereum and Hyperledger, but they have their own variation also. And one very interesting and popular one is called IOTA. So IOTA is a project that started a couple of years back, I think 2017. And although it is a distributed ledger solution, but it is actually not a blockchain per se. And one of the important things with IOTA is that it is meant for um, devices that are smaller in their footprint. Normally, devices that are uh, IoT enabled or IoT themselves. IoT is short for Internet of Things, which is the term given to any device that basically has a presence on the internet. So by presence, what we mean is that it has a legitimate IP address and it can be accessed either through a gateway or directly um, from other applications that are also on the internet. Examples are a Raspberry Pi or a wearable device or even uh, your cell phone. Um, Most typically in IoT devices are sensor devices, because till now we've not developed capability where devices can make transactions. So most of the times they take the role of reading the environment or observing uh, or basically initiating data ingestion transactions. So you could have an IoT device that senses people when they are probably crossing some location physically, or you could have IoT devices that are worn by someone who's looking to get their health metrics. So that device can be worn and then it senses various biometric matrices. Or you could have a weather sensing IoT device. So all of these devices, they basically, they're not active devices. They're not initiating transactions and um, operating anything. They're passive sensing or data creation devices that read some data and then translate it or send it to some sort of server or some location. Now, what IOTA proposes is that these devices can be actual transaction processors also, where if there is a value attached to the data that they are recording or sensing, then these devices should be able to market that data. And to be able to do that, we need to have a blockchain node or some sort of a transaction processing capability on these devices. Now, since they are small, their memory and processing capability is not huge like a desktop or a server. So normal Ethereum or Bitcoin nodes cannot work on these devices. Is there a question? You can type it out in chat if.
No, sir.
Um,
This the disturbance by mistakenly done.
okay, no problem. All right. So going back to our discussion, what IOTA proposes is that there should be a way to make these devices ledger compatible, or there should be a way in which these devices should be able to process transactions also. And to be able to do that, we have to reduce the processing requirement for a distributed ledger node, because you cannot run a full-blown Bitcoin node on an IoT device. So IOTA proposes a blockchain structure or a distributed ledger structure that is fundamentally different than the typical chain of blocks structure that regular blockchains have. So we've been talking about stack of blocks and sequence of blocks or chain of blocks where one block appears after the other one, that kind of structure. What IOTA says is that instead of such a simple structure, there should be a structure that is like a tangle of transactions or a tangle of blocks, all carrying one or more transactions that do not have any relationship between each other, but just a relationship with their predecessor. So you can kind of try to visualize that through the diagram that's out here. It's an acyclic graph. It's a graph where there are numerous nodes and vertices that's progressing from right to left as more such boxes get added to it. So think of this box as a node, as a block. So all of the different nodes that are running the IOTA ledger, they will be creating their own nodes, their own blocks. They will be adding it to the previous block that they have, and not caring about what other um, nodes are doing. In such a scenario, what we end up creating is a structure like this. Now, how do you control this is through a process called milestoning, where you create like uh, a boundary um, where all of the different blocks coincide and then verify themselves and then restart tangling themselves into different uh, branches after that milestone is reached. So this is again an alternate kind of way of looking at um, the the whole idea of attaining consensus. What this helps you do is that instead of all of these different um, nodes requiring to communicate with themselves to provide a sort of a singular and deterministic data structure, we are lenient enough to let the data structure proceed um, in different ways, uh, controlled by different nodes, and only kind of reconcile everything in certain frequencies, like maybe once in 50 days or once in 100 days or something like that. So if we look at like a very basic difference between these two structures is that there is only one tip when it comes to Ethereum or Bitcoin blockchain, but there are multiple tips. And tip is a technical word in IOTA data structure. So we have these tips that are basically heads of different transaction sequences. And what we aim to do is, number one, allow these tips to keep progressing on their own path. And then at some point, coalesce them or merge them into a single um, sort of a milestone snapshot process, and then reallow them to diverge. Now, for such a system to be enabled, what needs to happen is that there are some well identified nodes that keep track of all the tips, so that whenever there is a need, those tips can be identified and merged. And these nodes also have to ensure that no transactions get submitted during that milestone period. So if we want to explore that of it further. The tangle is not a single chain, which is basically the very fundamental point of difference. It is a network of parallelly processed transactions, just like we saw multiple chains getting created. And the process of adding a transaction is called attaching. And you would be attaching your transaction to a certain tip. And at one point, there are many tips that you can, select from. So this makes the whole um, data structure very scalable. The only thing that is enforced is that when you attach a transaction to a tip, what you have to ensure is that um, you verify the previous two transactions through a process very similar to proof of work. So you, let's say you're running a very small device, and that device collects some data and it wants to put that data on the IOTA tangle structure. They create a transaction to do that. That transaction can only be submitted if a proof of work of execution of, you know, or verification of two transactions that have been done prior to that new transaction in the same tip, they are verified. And that is not very difficult for the device because it's just executing a very small computing exercise. So any device with a very small memory footprint and processing footprint can very easily attach IOTA transactions. So having said that, um, if we want to analyze the transaction a bit further, IOTA transactions are slightly different than regular transactions on blockchains. So an IOTA transaction could be just a value transfer transaction, very similar to the Ethereum scenario where all you're doing is transferring ethers. You're not executing any smart contract. We discussed that earlier. The other kind of transaction would be the data transaction. One thing that needs to be understood about IOTA is that it does not support smart contracts. It only supports um, data transfer that IoT devices can generate. Although they're talking about introducing um, some sort of a smart contract capability, but that's not there right now. So uh, what you would be expecting is that the transaction will have some data, and that data would be stored on the IOTA ledger. And the reason why IOTA is so popular, or not really so popular, but it's so well suited for the IoT devices, is that it kind of aligns with the idea that a device should be able to just accept data that it's sensing and create transactions very, very quickly and then put them on the IOTA ledger. I mean, that's the basic goal that IOTA aims to achieve, allowing different devices, IoT equipment, remote sensing equipment to sense data and populate the ledger. Now, Since IOTA is using proof of work for validating two transactions in the past, um, it is definitely slightly wasteful. But when it comes to its comparison with something as expensive as Bitcoin, expensive in terms of requiring computational power, then IOTA doesn't even compare. It's probably 1 millionth the amount of effort or the amount of expense needed to verify IOTA transactions. And this is the reason why IOTA is able to offer a transaction fee-less operation, because it does not take the device a lot of effort, or the device need not basically do anything beyond just keep a small amount of processing power at its disposal to be able to submit an IOTA transaction. So the fees that the device requires is actually negligible, or it's not even in the context. There's no business use case for supporting something like that, that you would pay fees to a device owner for accepting transactions, which is why IOTA is primarily feeless. You can submit as many transactions as you want. Um, you'll not incur any fee, which is again a big difference between IOTA and some of the regular um, blockchain platforms that we've been talking about. Now, so we will not be discussing IOTA in much detail. We just want to use it as a reference to understand um, some of the other important blockchain platforms. Our focus will continue to be Ethereum and Hyperledger in the coming sessions. One of the things that as developers we need to understand is that IOTA is very much like other blockchains when it allows for creating a client and operates on wallets and then gives that explorer experience. So if you want to, let's say, take a look at all the transactions that are out there, there are two explorers, one for test environment and one for development environment. That gives you a similar view where you've got, I mean, you can think of milestones as blocks also. So you've got these major milestones that have happened in the past. Milestones exactly in the way I had described it, where all tips merge together. And then you've got these different message transactions. You will look at one transaction just like we did for Ethereum. So the content of this transaction is this. And you can read about this transaction. It is not a value transfer, which means that it's just about data transfers. And if you want, you can look at like the data that's there in the transaction by downloading its JSON equivalent, which is basically this. Now, one thing that needs to be additionally understood about IOTA is that it is using a computational technology or cryptographic computational technology that is quantum safe. So we've been talking about hashes and cryptography and everything. Um, One thing that needs to be understood is that although Bitcoin hash capability, which is SHA-256, it is very secure in itself. But if someone gains enough computing resources, then they can brute force SHA-256 to be able to identify the nonces very, very quickly. What that means is that given enough resources, Bitcoin blockchain can be taken over. We've been talking about how much those resources are going to be and how we practically solve the problem. But uh, quantum computing, which is an area of research, it promises that it is possible to mobilize those resources without um, the anticipated huge amount of investment. And if it becomes practically possible to mobilize that many resources, then the whole concept of proof of work blockchains that becomes vulnerable to that problem. What that means is that you'll be able to arrive at the right nonce very, very quickly. In fact, so quickly that you'll be able to replace the blockchain. That means everyone's bitcoins will be lost. The only thing that's protecting everyone is to be able to do that, you'll have to spend trillions and trillions of dollars, and the return would be just billions of bitcoins. Now, if that trillions and trillions of dollar figure comes down to billions, then that's a challenge. And quantum computing kind of proposes to do that. Not right now, but maybe in some near future. But IOTA is a technology that uses wallets that are using quantum safe computing. So they're using cryptography construct called Lamport um, in Lamport hashing scheme, which has been proposed by a cryptographer called Lamport, which is a 3-bit um, 3-bit computing. So we have in our hash calculations, we use 2-bit representations of the data that we compute the hash for. In IOTA wallets, we use 3-bit or ternary computing, where there is 0, 1, and then there is a -1. So that makes the problem of reverse engineering the hash um, again practically impossible even for quantum computers. But having said that, that's not something that we need to worry about now or for the coming future. Maybe at some point of time, that's something that we may have to deliberate on. So again, taking a quick pause for questions, thoughts, or comments. So I'd be really happy if there were some questions. Kind of convinces me that um, I'm reaching across. Okay. In that case, let me jump to the next agenda items. We might finish early. I was anticipating some questions on IOTA because it's an interesting sort of segue from the whole legacy blockchain discussion. But feel free to interrupt me with your questions. If we continue without questions, I might reach the end of my agenda for today sooner than expected. We'll have like 15 minutes to spare. So the next platform of interest for us is EOS. So
Excuse me,
EOS,
sir. Excuse me, sir.
yes, please. Go ahead.
Sorry, sir. Is there anyone have doubt? They can ask it.
I think there's a chat question. I'll repeat the question for everyone. Is that a case where IOTA can replace Ethereum due to its low computational cost, even in non-IoT environment? Yeah, definitely. So it is a very real possibility. The only reason why um, Ethereum is still popular is because IOTA does not support smart contracts. And Ethereum smart contract capability is very advanced. It offers um, an instruction set representing the smart contract, which is Turing complete. So what that means is that it's a complete programming language in simple terms. It can run loops. It can run conditional statements. It can manage cryptocurrency. It can call other contracts. Uh, One major problem with IOTA's underlying data structure is that um, there is no single timestamp that is common to the entire data structure. What that means is, let's say we looked at that tangle structure where there are different, I mean, it's easy to kind of think of it as different blockchains, you know, each progressing at its own pace. So if there is a timestamp at which block A gets committed on one blockchain sequence, the other blockchain might be committing it at timestamp B. So they don't know that which block came first because they have no common notion of time, which is why sequencing these blocks is a challenge for the acyclic graph data structure that we've got there. So this timestamp problem and the ability to run smart contracts in this data structure, because when we talk about smart contracts, we'll have to deploy it and then allow either the device to execute it or expect the device to become bigger to be able to have an execution environment. All of these challenges make it very difficult to uh, um, kind of make IOTA smart contract enabled. But at the same time, devices are becoming more powerful day by day. We've all heard of Moore's law. So at some point, there will definitely be a situation where um, IOTA can become a very important blockchain type, not replace Ethereum, but at least become a top contender. So thank you for that question. Anything else anyone wants to say, comment on? Okay, cool. So let's get back to the next application. So EOS is another blockchain type. And I mean, we've studied different blockchain flavors: Ethereum, Bitcoin, IOTA, Hyperledger. What we've understood is that the common underlying structure is um, the ledger that basically puts a system as being counted in the blockchain category. The other thing is the different way in which consensus is achieved. So we talked about election-based consensus when we were talking about Hyperledger. We talked about um, two transaction verification mechanism in IOTA. We talked about proof of work in Ethereum and Bitcoin. The differentiating factor that EOS has with some of these others is that it uses a proof of work, a consensus mechanism called um, delegated proof of stake. So um, just to, before I define what delegated proof of stake means, just to give you a high level idea of what EOS is, it is again a configurable blockchain, very similar to, but not entirely like Hyperledger. It is a public blockchain. It allows for building smart contracts, and it has a special smart contract toolkit. And its core implementation is what manages the building of blocks and the system layer. The smart contract implementation is not a part of the core layer. It is like an open source, not really open source. It is another system that you deploy on top of it. The differentiating factor is this consensus called delegated proof of stake. Before we understand what is delegated proof of stake, we need to understand what is proof of stake. So proof of stake, or POS, is an alternate to proof of work as a consensus mechanism. So proof of work basically identifies the honesty of a node. And one of the ways in which a node says that it's honest is that it executes that repeated brute force hashing. A possible alternate mechanism could be that that node kind of identifies itself as honest node by saying that I have a lot to lose if I become dishonest. So how will a node get lot, the question is that how will that happen? So the only way that happens is that if the node itself is custodian to a very large or sufficiently large native cryptocurrency, which will become valueless if the node becomes dishonest. Think of it this way, and this is a simple but practical example. Anyone who is invested in a project, like let's say we are all investors and there is a project and we all invest some money because we think the project is going to be very successful and we'll get some returns on it. Just by the fact that we have invested in the project, we will be very keen to see that project succeed, and we'll do our level best in terms of promoting the success of the project. Now come back to our blockchain and the Byzantine fault tolerance situation. What if we are able to make the network hold that investment in the network's honesty by ensuring that the important parts of the network that are running, big nodes in the network, they themselves are only allowed to participate in the network if they can show that they are holding a major investment in the network. So in the Ethereum world, it would be, let's say, a node that holds 500,000 ethers is the only one that's allowed to submit blocks, because that node will always submit right blocks so that Ethereum blockchain does not fail. So that is like another take on how we can get honesty from the network by making them a part of the success of the network. The moment, let's say someone is able to hack a proof of stake network, then the important stakers in the network who are holding investment, their stake will become, that will depreciate or may lose the whole value. So they will not allow anyone to subvert the network in any way. And they themselves will always be honest so that the value of their investment is intact. So that's proof of stake for you. How does proof of stake or how does delegated proof of stake work is that you select a number of nodes that have enough proof of stake or who have enough stake, and then let them delegate other important nodes. So it's just like one level of indirection. That's saying that instead of the proof of stake node submitting the block, we let the proof of stake node select someone who will submit a block or delegate that authority to someone else. So that is DPoS or delegated proof of stake. And EOS implements it as their core consensus mechanism. So along with that, EOS supports WebAssembly for building smart contracts. WebAssembly is a sort of an assembly language that works on the browsers. And it's got a contract development kit, CDT, that you can download and start building contracts on it. So that is the extent of discussion we'll have on EOS. Just another sort of reference blockchain implementation for us to look at. Any other questions?
Dear participants, if you have any question or any doubt, you can ask it.
So I just have 3 more slides, after which we will basically wrap up. The agenda for today is done.
Sure, sir.
I will again leave the open floor for questions, and feel free to think of your questions. Like, we'll finish in another 6-7 minutes. So we'll have good 10 minutes to have a discussion. So you can, start thinking of your questions if you want to like gather your thoughts. So the next important blockchain flavor is multi-chain or multi-chain. And multi-chain is basically a fork of Bitcoin blockchain. When we say fork, it's basically a branch of that Bitcoin blockchain that's running, which allows you to deploy some very simple smart contracts on the Bitcoin blockchain. So although it's not directly deployed on Bitcoin, on the Bitcoin blockchain, but there is a layer on which we maintain some sort of smart contract capability that uses the underlying Bitcoin blockchain to verify transactions. So a very simple way to think of it is that, let's say you build an application, and every time that application accepts a transaction, you execute something in that application, but that transaction gets first verified by the Bitcoin blockchain. So you send that transaction to Bitcoin blockchain, and what Bitcoin blockchain says is that the transaction is verified, and then only you execute it. So you're not running it on the Bitcoin blockchain, but you're using the blockchain and its verification capability. So you can deploy it in both the private and the public contexts. It's very easy to operate. And what it does is it allows you to implement things like creating an asset, creating rules on that asset, then making some high level transactions on those assets, like issuing the asset to someone or selling that asset to someone or destroying that asset. So all of those high level things um, you can implement on multi-chain. BigChain DB. So BigChain DB is represented as BigChain in the agenda, the table of contents we have. It is again only a part of the blockchain idea. So it just talks about how you'd store those transactions. It allows for immutability through that same hash-based scheme, and it can work in a distributed, decentralized environment, and it can allow for transfer of assets. But it is just a data store. It does not run smart contracts. So you can define anything as a database entity, but you cannot execute that. You can transfer it, but not execute it. So it's kind of a simplistic blockchain solution that can work along with other blockchains. And then finally, Corda. So although we've spoken about Corda along with BigChain DB and multi-chain, but it is a very important uh, blockchain type or blockchain framework. Corda is used in the financial industry extensively, and it is a private blockchain, and it focuses on transaction data privacy. It, in fact, is so well positioned when it comes to um, data privacy is that it doesn't even allow all the nodes to have the same data, although that is the underlying principle of the blockchain, but it only stores that data on the node on which that node has access. Some of the other features are that it supports smart contracts, and it works very well with Java and Kotlin. Both of them are languages focused towards the JVM or Java Virtual Machine environment. And then it has a concept called notary, which is a validation process to ensure something very similar to what the orderer does. So we talked about orderer in Hyperledger. Notary is something very similar. And the applications that we build on Corda are called CordApps. So that's Corda for us. Again, a very interesting project. I would encourage those of us who are familiar with Java to explore Corda. So with that, we come to the end of what we wanted to discuss today. I would again implore you to come up with your thoughts, questions, or any suggestion on how we want to move forward. And I will be happy to accept your suggestions.
Hello, sir.
Yes.
Sir, is there any network map of Corda is available?
You could you repeat that? Network map?
Network map of Corda
Network map. You mean like
means
a
how
diagram?
means how we can collect the data.
Okay, so Corda is a private blockchain. You will have to deploy it. It's not like Ethereum or Bitcoin where you can go to the Explorer and you can look at the transactions that are being submitted by people. It is deployed by companies internally. Think of it like an ERP. Companies do not expose ERP data externally. So I'm hoping that you mean you want to see the transactions on Corda.
Yes, sir.
Yeah, so yeah, that is not possible unless
Sorry, maybe.
but that's a good question. Hope that answered it.
Yes, thank you, sir.
Any other questions?
Is there any participants who has any doubt? They can ask it.
So good afternoon, sir. This is related to the, I think I have already asked this in a first session as well. What is going to, what about the outcomes of transactions? Are they going to store on the same block, or it will create a new block when it comes to the smart contract results? So are they going to update the block, or they are going to create a new block, which is again, I think it's related to the first session discussion. I think that is related to the rent agreement, which example which you have given. When I make a call to pay rent function, then what exactly that function's results are going to store?
Yeah, so that is a good question again. And I accept that we only answered it partially. So the result of a transaction is, so there could be two results. Either the transaction just runs um, and observes the blockchain. It just reads some data from the blockchain and returns it to the client. In which case there is no result. The blockchain stays as it is. The client just gets a view of the data and the client might use it. The other kind of transaction would be the update transaction, where the blockchain smart contract gets some kind of an update. That update is stored along with the transaction on the blockchain. And it is stored in an area that is kept for contract memory. That area is a part of the blockchain itself. When it comes to Ethereum, the structure is not as simplistic as stack of blocks. The structure is that there are different types of blocks that are merged together, and then they separately create like a block with its data and the transaction entries and potentially also balances of accounts that got operated upon in that block. So Ethereum has three kinds of data: state trie, which is basically the tree structure of the state of the blockchain; the account trie, which is the tree structure of account balances; and storage trie. Storage trie is a tree structure for contract storage. Now this contract storage is where whatever smart contracts you deploy, if they have to store anything, they keep it in that storage, in that area. And any transaction that goes on to update parts of your contract, like maybe if you're talking about rent, maybe your contract will have a field called rent amount, and that rent amount has to be increased after 6 months. Then there is a transaction that goes on to increase that rent amount. That increase is going to be an update to a variable that's stored in the storage area. So earlier that variable maybe was 500. Now it becomes 600. So the storage will have 500 mapped to the timestamp at which it was 500, and then another entry for 600. So the latest value would be 600, and all of it is going to be on the blockchain. And I still realize I'm just talking, I'm not demonstrating that, which I will definitely do the moment we are actually running smart contracts. That's the first thing I'll do. So hopefully that kind of answered your question.
Yeah, sure. So I think the contract will not be updated. It will maintain a variables, and that will get stored in the storage areas.
Absolutely, you got it.
Okay.
Yep.
Thank you.
Thank you, sir. Is there any other participants who have doubt or want to ask anything in the context of Corda or Solidity? So we are wrapping our session here. Tomorrow on day 3, we are meeting at 10 a.m. where we learn about the digital currency, cryptocurrency, that is taught by Yash Sharma only. So thank you very much, sir, to share your fruitful knowledge with us on the context of blockchain in the area of the Corda and Solidity. Thank you very much, sir.
You're welcome, and thank you for joining. Thanks.